So we've introduced the vector product and angular momentum, and we said that angular momentum is the cross product, the vector product of the radial vector to a point with the momentum vector at that point. And we also said, in terms of magnitude, that this angular momentum is equal to the linear momentum times its moment arm, the shortest distance to the line of action of that momentum from the axis of rotation, or the origin that we're considering. And that could be a constant. If it's moving in a straight line, then that distance to that line of action could be a constant, and the angular momentum could be a constant as well. We could have a constant as well if a planet were going around the sun and changing its orbit. Planets go around the sun in elliptical orbits, and sometimes they are closer to the sun and sometimes they're further away. And so at any particular point, their angular momentum is going to be their mass times their velocity times their orbital radius at that point. Well, if it's equal at different points in this orbit, and the mass being the same for the planet, we would have the relationship that the linear velocity times the radius of the orbit at that point is a constant. So as the radius gets smaller, the velocity gets faster, and vice versa. So as this planet's going around the sun, when it gets closer to the sun, it moves faster, and then when it gets further away, it moves slower. Faster and then slower, faster and then slower. A comet does the same thing, only the ellipsoid is much more smooshed, so that in a comet it goes way out to the outer solar system, stays there for years and years and years, and then sometime it comes in, whips around the sun, goes way out there, stays out there for years and years and years, whips around the sun, that sort of thing. But angular momentum is conserved. The radius of the orbit at any particular point times its velocity will be a constant. If we were to differentiate the vector expression for angular momentum, take the derivative of the angular momentum, we would have to distribute this derivative to the two vectors. So we have dr dt crossed with the momentum and r crossed with dp dt. But dr dt is simply the velocity. So we would have velocity crossed with the momentum, mass being a constant. We have velocity crossed with velocity. Any vector crossed with itself will be 0, so this first term is 0. Second term is r crossed with the change in momentum per time, and that is r crossed with the force. And we know from our first definition of a cross product that the radial vector crossed with the force at that point is called the torque. So the derivative of the angular momentum vector is equal to the torque vector. How about that? So the change of the angular momentum with respect to time, the rate of change of that, is equal to the torque, just like the rate of change of momentum with respect to time is equal to the force. In other words, this is Newton's law in momentum form, second law, and this is Newton's second law in angular momentum form. How about that? So we're still making our analogy between linear motion to rotational motion, and all the equations seem to be of the same kind of form. We just have different variables. It is also true that angular momentum is equal to the moment of inertia times the angular velocity. And note how similar this looks to linear momentum. If we substitute mass from linear momentum to moment of inertia, and we substitute in for linear velocity, angular velocity, we get from linear momentum, angular momentum. So they have the same form as well, and those are logical substitutions, where the moment of inertia plays the same kind of role in rotations as mass does for linear motion. In other words, resisting changes in its motion or inertia. Also note this verification of net torque. If I were to take the derivative of this form of the angular momentum, I would have, assuming that our moment of inertia were constant, the moment of inertia times the derivative of the angular velocity with respect to time, which is indeed the angular acceleration. So torque would be equal to the derivative of the angular momentum with respect to time, and that's equal to the moment of inertia times the angular acceleration, which is what we got before. Here's our rotational to linear transformations. For a linear displacement along an arc, it's equal to the angular displacement of the arc times the radius of the arc. Linear velocity is equal to the angular velocity times the radius. Linear acceleration is equal to the angular acceleration times the radius to that point from the pivot. Torque is equal to the perpendicular force times the radius to that point. And angular momentum is the perpendicular momentum times the radius to that point. These are all rotational to linear transformations. Angular momentum is conserved if there is no net torque on the system. If there's no external net torque on a system, the angular momentum of that system will be conserved. So we would say our initial angular momentum would equal our final angular momentum. And that would mean then that our initial moment of inertia times our initial angular velocity would equal our final moment of inertia times our final angular velocity. Now, in these cases, it's sometimes more easily done to change your moment of inertia and hence change your angular velocity if your angular momentum is conserved. A good example here done by Medusa, who was a good sport. I kind of like Medusa. She just had one bad hair day in history, and she's had to pay for it ever since. But she's a good sport. She's going to demonstrate this principle of angular momentum. She's holding these weights out, and if she were given an initial angular speed, she would have an angular momentum equal to her moment of inertia, herself with the weights, times her angular speed. If she were to pull those weights in, that would greatly reduce her moment of inertia, and hence her angular speed would have to increase to compensate, giving her a constant angular momentum. Why would that greatly change her moment of inertia? Well, she's going to have a certain moment of inertia associated with her body. We can almost think of that like a cylinder, 1/2 mr squared. If we were to calculate that, we'd get some kind of value. But if you take these weights and you hold them out like this at some distance away, that moment of inertia goes up by mr squared. And the r squared value of that distance away from the axis is pretty significant. So even though these masses are much smaller than the weight of the body or the mass of the body, they would have a lot more moment of inertia associated with them because they're so far away from the axis. So if I start out like this with a certain moment of inertia and then I bring it in, I move faster. I had to stop myself. If I move faster because I reduce my moment of inertia, my angular velocity increases significantly. I'm going to try that again. Give myself a little bit and pull this in, I move faster. Actually, it could be a factor of 6-7 times as I move those in. And that's what an ice skater does. When an ice skater is moving around, he or she puts their arms way out here, and even though there's not a whole lot of mass associated with the arms, the fact that they're so far away from the body, and given that r squared term, really increases the moment of inertia. So as you start to spin like this, and then you bring your arms in, you move a whole lot faster as you reduce your moment of inertia. Here's the bicycle spinning wheel. we have a certain amount of angular momentum associated with spinning a bicycle wheel. And if you were to suddenly change that direction, the whole system would have to turn to compensate. There's a lot of friction in this chair, so it's not working as well as it should. But angular momentum tries to stay conserved, so as I flipped that, I changed the angular momentum of the wheel, and the whole system had to compensate to maintain constant angular momentum. But in this case, there was an external torque on the system. That's the friction of the chair. Let's try a problem. A uniform solid disk of mass 3 kilograms and radius 0.2 meters rotates about a fixed axis perpendicular to its face. If the angular frequency of the rotation is 6 radians per second, calculate the angular momentum of the disk when the axis of rotation passes through its center of mass. Well, we have a disk, and the moment of inertia of a disk is 1/2 mr squared. So, calculate that. That's going to be 1/2 times 3 kilograms. Radius of the disk is 0.2 meters squared, 0.06 kilogram meter squared. Now, multiply that by its angular velocity, and that'll give us the initial angular momentum through the center of mass. So 0.06 times 6 radians per second, 0.36 kilogram meter squared per second is our angular momentum for this disk. A 0.5 kilogram piece of putty is dropped vertically onto the rotating cylinder of part A at a point 0.1 meters from the center of the rotation. It's going to come down about midway between the disk, midway between the center of the disk and the perimeter. Determine the final angular speed of this system. So with that extra putty falling down on this disk, we're going to increase its moment of inertia because it's going to have this extra mr squared term due to the putty. That's going to increase the moment of inertia. If angular momentum is conserved, the angular speed should reduce inversely proportional. So our initial angular momentum is 0.36 kilogram meters per second, but our new angular momentum is going to be our new moment of inertia, the moment of inertia of the cylinder plus the moment of inertia of the putty, mr squared. That's going to be 0.06 for the disk, plus the putty was 0.5 kilograms and it's 0.1 meters away from the axis of rotation squared. So that is a new moment of inertia of 0.065. These two angular momentums should be equal. So we have 0.36 is equal to 0.065, and our final angular speed will be 5.54 radians per second. So it was moving at 6 radians per second. A little piece of putty fell on it, changed its moment of inertia, and now it's rotating at 5.54 radians per second. So we have looked at a lot of rotational motion, and we can find that there is a lot of analogs of rotational motion to linear motion. We have our 5 kinematic equations that you know and love for linear motion, and we have 5 rotational kinematic equations that you're learning to love for rotational motion. The only thing we've changed is our variables, but the form of the equations are exactly the same. For linear motion, we have a bunch of different other formulas. We have kinetic energy, we have momentum, we have Newton's second law, the summation of all the forces equal ma. We have Newton's second law in momentum form, forces equal to the change in momentum per time. We have work, which is the integration of a force over a displacement, dx, from initial to final. We have the same kind of form of equations for rotational motion. Rotational kinetic energy, 1/2 moment of inertia times angular velocity squared. Angular momentum, moment of inertia times linear angular velocity. Newton's second law for torques, The net torque is equal to moment of inertia times angular acceleration. Net torque is equal to the change of angular momentum with respect to time. And work is equal to the integration of torque over an angle. All these are analogs of linear motion. That concludes the second lecture of Chapter 11. Try your hand at some of the problems in the problem sets.